started. Last time we talked about the driving force of filtration. So the driving force comes from the heart. That's the pump. So the heart working hard, push the blood through the renal artery, eventually go to the efferent arteriole, and it go to the glomerulus. Glomerulus is like a balloon there. When you push water into the balloon, you have a hydrostatic pressure. Okay, well, there's the pressure to push plasma out. So that's the main driving force. This 55 millimeter mercury hydrostatic pressure, that's the driving force for filtration, push the plasma out. And you have two forces that are working against filtration. One is the hydrostatic pressure of the fluid in the Broman's capsule. Every time you have a liquid in a bowl, you create a pressure. And when you filter the liquid from the glomerulus into the Broman's capsule, you have liquid in the Broman's capsule. Okay, you have a bowl, you have liquid, you have pressure. And this pressure will work against filtration. It's about 50 millimeter mercury. The third one, osmotic pressure. Filtration is a non-selective process because they don't have time to make it selective. They don't have time to put membrane proteins on the Broman's capsule and decide which molecules moving in, which one don't move in. It takes too long. It could not. So they just create a slit. Every time this molecule is smaller than a slit, move in. And if it's bigger, stay out. So big proteins, red blood cells, they stay in the glomerulus. They won't be able to be filtered into the Broman's capsule. And that creates an osmotic pressure because the water will be filtered in. And when the water stays in the Broman's capsule, they see, oh, there are so many proteins inside the glomerulus. They want to move back to dilute those proteins. Water always feel like it's their job to do, to dilute. So this also works against the filtration. So three forces, two against, one for filtration. And you take 55, subtract 30, subtract 15, you have 10 millimeter mercury. This small force create a net filtration pressure, provide a consistent force for filtration to happen. But now you are facing a problem. The problem is your pump always varies its pushing force. When you start to exercise, your blood pressure increase, cardio output increase, because sympathetic tone increase. When you're resting, blood pressure decrease. So this pushing force always change. But you want this filtration to be constant. So today, our first topic, we'll talk about how to regulate this part to make sure the filtration is constant. You don't want this to change too much because if this fluctuates too much, you damage this filter. You want this filter to be able to run for 80, 90 years. Okay, so this is the driving force for filtration. And the filtration rate is called the glomerular filtration rate. Clinically, we use this to represent your kidney function. It's about 125 ml per minute or 180 liter per day. Usually they like to use the liter per day, about 180 liter per day. And that's a lot. You have about 5 liters of blood and 180 liter per day. So you clean all the blood less than 30 minutes. They've been cleaned once. And when the bloods go there, not all blood will be cleaned at the same time. It's every time about 20% of the blood really go into the Broman's capsule, about 20%. So let's look at the picture. Through the efferent arteriole, the blood come to the Broman's, to the glomerulus, and actually only 20% of them will be filtered. The other 80% will go through the efferent arteriole, go to the peritubular capillary, and eventually go to the renal vein. And those 20% being filtered in, over 19% of them will be taken back. Because once they go into this tube, they're going to take the water back, they're going to take the glucose back, the sodium back, those important molecules being taken back, so they become clean blood. So in your kidney, you have those old blood, those dirty blood mixed with those clean blood. They just mix together. But that's all right because you constantly running this filter, so eventually all blood will be clean. It's those renal vein, when the blood flow out, is 80% old with 20% new. And you have less than 1% become your urine. So they filter 180 liter of blood per day. You don't pee 180 liter of urine per day. You pee around 1 to 2 liter of urine per day. So that's less than 1%. And this can be even smaller when you are dehydrated or severely dehydrated. So when you forget to drink water, you don't use the bathroom for hours. You don't produce too much urine. For those people that got lost in the desert for days, they are severely dehydrated. They're going to produce 0 urine. They don't pee. And that's not good, right? It can cause the kidney failure. And also, if it's still not working good enough, eventually the brain going to shut down the sweating system. Because even though they have no pee, they still sweat. And you still breathe out water. When you breathe out water vapor. And when they shut down the sweating system, or this person can easily have heat shock. So people with heat shock, their skin, if you touch the skin, is dry. They have no sweating. So the body try to conserve water. We'll talk more about that in the water balance. So my point here is you secrete less than 1%, or even less, can be almost zero, or extreme case, it can be zero. So next time when we do the calculation, calculate the renal clearance. That's how good this machine is working to clean your blood out of certain molecule, the renal clearance. We have to make a small assumption, which is the excretion. We make this zero. So like we dump 100% blood and 100% being processed here, see what happens. They just assume this to be zero. And it's not too far away from the truth, because you actually have less than 1% or even less being excreted out. Now let's look at the GFR regulation. You want the GFR to be constant. You want the GFR to be constant. Every time you change the GFR, well, you can damage this filter. And the way to regulate it is actually pretty straightforward. We talk about the regulations in Unit 3. Vasodilation, vasoconstriction. You want to change the balloon size. You want to make more water, less water flow into this balloon, this glomerulus. Well, you just dilate or constrict the efferent artery. This is the main place. This is the main place to regulate. Say the blood flow through the efferent arteriole, go to the glomerulus. When you dilate the efferent arteriole, resistance decrease. We'll talk about that in Unit 3. And more blood automatically go to the glomerulus. Then GFR will increase. The update, when you constrict the efferent arteriole, resistance increase, then less blood flow to here, the balloon becomes smaller, then hydrostatic pressure decrease, GFR decrease. And you want the GFR to be constant. So the way they work is, say you start to exercise. Because you activate your sympathetic nervous system, your cardio output increase. So your blood pressure increase, then blood flow gonna increase. Right? In that situation, you will constrict the efferent arteriole. So the GFR is still constant. And when you're resting, you're sleeping, your blood pressure decrease. When your blood pressure decrease, less pushing force to here, and then the GFR gonna decrease. Okay, you dilate the efferent arteriole. Then more blood can go to here, and GFR still maintain consistent. That's how they regulate the GFR through the efferent arteriole. And they can actually regulate the efferent arteriole. Say when you dilate the efferent arterioles, more blood go to here, you can constrict the efferent as well. It'll be the same effect, less water leak out of the balloon. And when you need to constrict the efferent arteriole, make less blood flow here, you can also dilate the efferent arteriole, more blood flow out. The balloon is also smaller. So you can work on the efferent, you can work on the efferent, but they need to be different. But most of the time, the efferent, that's the main place. That's the main place. Main regulation happens in the efferent arteriole. And through this kind of regulation, the GFR is actually very consistent in the body. The result is this. The x-axis tell you what's your mean arterial pressure. The y-axis is the GFR. And in Unit 3, you learned how to calculate the mean arterial pressure. And normal people, their mean arterial pressure is about 93 millimeter mercury, because the systolic pressure is 120, diastolic pressure is 80, and the mean arterial pressure is about 93 millimeter mercury. Okay, their GFR is 180. And when they start to exercise, their blood pressure increase because cardio output increase. Well, still 180. And when they relax, they go to sleep, their blood pressure drop a little bit, well, GFR still 180. You want the GFR to be constant. You don't want this to fluctuate because you're gonna damage your filter. And it turned out not just in this range, as long as this person's blood pressure stay between 80 to 180 millimeter mercury, GFR is constant, 180 liter per day. That's amazing job. That's a pretty amazing job, because for most of us, our blood pressure never go out of this range. Your blood pressure go over 180. That's hypertension. It's not just hypertension, that's extreme hypertension. This person's systolic pressure probably gonna go to 200 to reach their mean arterial pressure 180. Then this machine is out of control. They could not maintain the GFR anymore. Or this person's blood pressure have to drop to 80 millimeter mercury. That's pretty low. For most of us, our blood pressure don't go to this low. If you go to this low, means, well, this person is gonna have hemorrhage. He's losing blood too much. He can drop to this low. Or this person have heart attack. His heart stop for a while. And this can be dropped to zero. Right? When you have no cardio output, the blood pressure will be zero. But most of us in our whole life is staying in this range. That's how good your body maintains GFR. And when you drop to be too low, yes, you have difficulty maintaining GFR. So clinically, we do have some people, they have a heart attack, they have other disease, and suddenly their heart stopped, they be brought back, and their heart started to function, but their whole life they need to do dialysis. And you say, well, the heart is here, the kidney is there. Why they affect? Because the blood flow, the blood pressure is the main driving force of GFR. So when the blood pressure stay to be so low for so long, then this filter machine just won't be able to run normally. So they have to do dialysis. They can damage the kidney. But for most of us, our whole life, our GFR is well maintained. Most of us in the whole life, it never go out of this range. So we know these results. Now let's ask how. Etiology, we keep asking how to make this happen, how to maintain the GFR. And we can put those mechanisms into two categories, local and systemic. So let's look at the local first. Local play a bigger role. In our body, we have several local control. So this is not the first time we see the local control. In unit 3, when we talk about, okay, you want the blood to flow into more blood flow into this organ. Say when you're exercising your six-pack, you want more blood to go to your six-pack. And next second, you start to work on your trapezius, your back muscle. You want more blood to go to your trapezius. And the next minute, you go to run and you want more blood to go to your quadricep and hamstring muscles. So always change. And your body are able to do that because when you start to exercise your muscle and they metabolize it more, then produce more metabolizing molecules. Some of them are vasodilated, they can dilate the blood vessel. So more blood can go to the areas you are using. In unit 4, when we talk about oxygen, go to the lung, and lungs are alveoli, millions of alveoli. Even in a normal situation, not every alveolus can expand. Some of them don't expand. But the next time when you breathe, they expand. That's normal. So you want more blood go to those alveoli, they expand, they have fresh oxygen, so they can load oxygen, local control. And your body are able to do that because those arterioles, they sense the CO2. So they can cause the vasodilation, more blood go to that areas. And the next time, different alveoli expand, well, pattern change, local control. So local control is not new here. So local control, your body has several local control. So in the kidney, also the local control play a bigger role. And we have two local control, myogenic response, tubular glomerular feedback. And the main one, of course, that's the second one, tubular glomerular feedback. That's the main one. And let's look at the myogenic response. Myogenic response happens in the afferent arteriole. There's those afferent arteriole. They're arteries, so they're more smooth muscle, more plastic fiber, and they're like a rubber band. So when you push them more, they contract more. That's myogenic response. So when your heart increase the blood pressure, more blood sends through the afferent arteriole, they be stretched more, they contract more. So when they contract more, increase the resistance, decrease the flow. That's a myogenic response. And the second one is called the tubular glomerular feedback. This is the main mechanism. It's a feedback loop. It's negative feedback. The tubular glomerular feedback was still not 100% understood what's going on. They still study it. So we know the general picture. We know where it starts, we know where it ends, but how they communicate, we still not 100% understood. So the starting point is a group of cells called macula densa cell. Macula densa cells, their location is in the ascending loop. Ascending loop. And when we look at the nephron, start from the Broman's capsule, then proximal tubule, descending loop, loop of Henle, ascending loop. It sounds pretty far away from the afferent arteriole because they want to regulate afferent arteriole. But actually, they're not too far away. But we look at the picture because of the structure of the nephron. So the descending loop, it goes to very deep. When it goes to the ascending loop, the ascending loop, macula densa is actually right next to the afferent arteriole. So they're right next to it, neighbor. And when they've been stretched, it's when your GFR increase. When your GFR increase, more liquid being pushed into the Broman's capsule. It will go through this tube, descending loop, loop of Henle, ascending loop, and macula densa cells being stretched. Once they've been stretched, they release a paracrine signal. In unit 1, when we talk about the cell communication, and I say chemical signals can be put into 3 different categories. They're all chemical signals. But based on the distance they work, the shortest one is neurotransmitter. So neurotransmitter only work in the synapse, synaptic cleft, very short distance, nanometer range. And the longest one is hormone. So those chemical molecules released to the blood, they will be carried by the blood and blood go everywhere. Hormones, long distance communication, but they're all chemical signals. And we also have something in between. The one in between is called paracrine. So paracrine release chemical signals to their neighbor. They don't go to the blood. So it won't go through the bloodstream to your brain. And also told you your digestive system and the renal system use a lot of paracrine. So this one is paracrine. The macula densa cells release the paracrine signal. And it will be picked up by the neighbor. Then the granular cells in the afferent arteriole, they are their neighbor. So they can pick up the signal, they can cause the vasoconstriction, regulate the GFR. So that's how they work. That's where they're located. And the pathway, negative feedback. So this is tubular glomerular feedback. Start from the GFR increase, because GFR increase means too much blood come from the afferent arterioles. And this balloon become too big. That's why the GFR increase. So with the GFR increase, the flow from the glomerulus to the Broman's capsule increase and go through those loop, descending loop, loop of Henle, ascending loop. When they go to the ascending loop, they've been stretched more. So macula densas, when they've been stretched more, they release paracrine. And those paracrine signal can be picked up by the granular cells in the afferent arteriole. It will cause vasoconstriction. And we constrict the afferent arterioles, less blood go to the glomerulus and GFR decrease. So it's a negative feedback loop. In unit 1, when we talk about those loops, maintain homeostasis, I tell you in your body, over 95% of them negative feedback, because that's the one maintain homeostasis. So start from the GFR increase, it end up with GFR decrease, negative feedback loop. So that's the local control. And the tubular glomerular feedback played a major role in maintaining your GFR. Now let's look at the systemic control. Most of the time, your local control take over the job and do a good job in maintaining your GFR. Sometimes your systemic control will kick in. And we have two long-distance communication systems, nervous system and the endocrine system. So we have these two. The nervous system is sympathetic. It will cause vasoconstriction. The hormone systems, we have a hormone pathway called RAS, Renal Angiotensin II system. And the old textbook called RAAS pathway, Renal Angiotensin II aldosterone pathway. That's the old textbook. We will talk more in details next time. Maybe next week when we talk about or after the spring break, or not spring break, after the holiday, Thanksgiving. The sodium balance. That's an important pathway to regulate sodium balance. When renal is a hormone released by the kidney, and it will trigger, renal will turn angiotensinogen into ANG1, which is not a very important hormone. But ANG1 can quickly turn into ANG2. That's a super powerful hormone. And ANG2 can trigger aldosterone release. And aldosterone's job is sodium reabsorption. So that's the pathway regulates sodium. That's why the old textbook called RAAS, Renal Angiotensin Aldosterone. But gradually we found ANG2 is a very, very powerful hormone. It does not just trigger aldosterone release. It also do a lot of things like it's a vasoconstrictor. It also can talk to the other systems, regulate your body water. So the new textbook is called RAS, Renal Angiotensin system. And this will cause the vasoconstriction. So you found both of them will constrict the blood vessel. And when you constrict the blood vessel, you decrease the blood flow, decrease GFR. But I would say these two systems, when they kick in, their main job is not to control your GFR. They just want to decrease the GFR to get what they really want. What they really want is to maintain your blood pressure. When these two systems kick in, that's the situation you are bleeding, or you are severe dehydrated. And your sympathetic system and the nerve and the endocrine system, they are working like crazy to try to maintain your cardio output. That's the main thing. If you could not maintain your blood pressure, could not maintain your cardio output, you're gonna pass out, then game over. That's when the sympathetic system and the RAS system kick in, and they will conserve water. Conserve water is they ask the GFR, hey, don't pee that much, you're losing water. So there's the one of their effect is they will regulate your GFR. But when these two systems kick in, is you are in big trouble. You're in hemorrhage, you're in severe dehydrations, and they need to do something to conserve every little bit of water they can conserve. That's when this kick in. So usually local control, that's the big one to maintain your GFR. So we will talk more about the systemic control when we go to the integrative physiology. That's how your body all work together for you to handle those extreme situations. So we almost finished the filtration. The next slide, how is GFR used? We use it to represent the kidney's function. So when you do your annual health check, they tell you what's your GFR, and you want this number to be big. You want to have a big filter. You don't want your big filter turned into a small filter. Then they won't be able to clean your fish tank, which is your body blood. So you want this number to be big, represent the kidney's function. It can decide the renal threshold. Renal threshold is the concentration. Because the molecules, once they've been filtered in, your kidney have to take it back, like glucose, you want them to take it back. And the maximum concentration your kidney can handle is called the renal threshold. So renal threshold, just a concentration. There's nephron, filtration, happens here, there's filtration. And how to calculate filtration? GFR multiply the concentration of that molecule in the plasma, that's filtration. Say your filtration rate is 2 liters per minute, and you have 2 marbles of that particle per liter. Then I ask you every minute, how many marbles been filtered in? Just multiply these two together. So 4 marbles per minute. Because you have 2 marbles per liter, and every minute you filter in 2 liters. Okay, well then totally you have 2 liters of blood being filtered in, and then you have 4 marbles. And that's filtration. You just multiply these two together. And renal threshold is one of the concentration. That's the maximum concentration you can put into the system, and the system can still handle. That's the renal threshold. So the concept is pretty straightforward. It's just when we start to use the real numbers, say this is 180 liter, 179 liter per day, and this is 350 milligram per milliliter, and students start to freak out. But this is the concept. This is filtration. And the renal threshold is just one of the concentration. So for diabetes patient, you say, let me decrease this to 0. If you have no marbles in the blood, nothing will be filtered in. Yes, that will be great. But the problem is your blood sugar level is not 0. If it's 0, you're going to pass out, you will be dead. So you always have some blood sugar, and always they be filtered in, and they will be handled. And for kidney, the glucose handling is reabsorption. So reabsorption is take this molecule back. That's reabsorption. You take it back. So move from the lumen back into the blood, because you have peritubular capillary there. It will quickly go back to your circulation. And the filtration part is non-selective. You put a slit there. If the molecule is smaller than the slit, it will be filtered in. Then reabsorption is different. Reabsorption is the process from lumen back into the plasma. And it requires membrane protein. So in unit 1, we talk about how to transport glucose, how to transport sodiums. We talk about those membrane transporter. Those membrane transporter, sodiums goes to the sodium channel. And glucose, we can use the glucose carrier, or we use sodium glucose importer. And depends on their concentration gradient. Sometimes we use the passive transporter, glucose carrier. Sometimes we use the active transporter, the glucose sodium importer. Yeah, all of this can come back when we talk about reabsorption. Because this is a selective process. You don't reabsorb everything back. You don't reabsorb everything back. You only reabsorb something you want back. So this process is selective. And selective, well, the knowledge, you actually learn them in unit 1. So those unit 1 knowledge gonna come back here. And most of them, the reabsorption process is unregulated. So last time I showed you a nephron, the first 80% of them, they are purple, the last 20% of them, they are yellow. The last 80% of them, unregulated means they don't have to ask, should I take this molecule back or not? The answer will always be yes. Because you need to take over 99% of the molecule back. So the first 80% unregulated. But apparently your urine concentration varies. Your urine can be very concentrated like iced tea, or sometimes it's very diluted like pure water. That's the last 20% of the distal nephron. That's the regulated part. So it depends on your body osmolarity. They can decide to take more, take less. Let's take a 4 minutes break. Come back at 40. When the filtration happens, a lot of molecules will be filtered into the nephron, become lumen. So this yellow part is the lumen. A lot of small molecules are there. And if your body don't want it, yeah, it will go through this whole tube and eventually become your urine, you pee them out. So like those toxic molecules, your body don't want them. Eventually they show up in the urine. And people do drugs. Why take the urine sample? We'll find what you have in the body, because the blood will be filtered in and those toxic molecules won't be taken back. So we can use your urine sample and to figure out what you have in your blood. But all these molecules, you need them back. Sodiums, waters, an ion, like bicarb, it's very important, an ion, maintain your body pH is buffer. And those potassiums, calcium, urea, all these are important molecules. So you have 20 different kind of marbles in the lumens. You want to take all these 20 marbles back. Which one come back first? And the answer is sodium. Sodium is a very important molecule. It's so important. We are always looking for sodium. You say, oh, I don't feel like we are always looking for sodium. I actually have too much sodium. Yeah, that's in the past 100 years, our diet totally changed. But think about animals. It's very difficult for the animal to find sodium. If you give them a sodium rock, they will lick it. They're always looking for sodium. They can only find the sodium from the some fruit. They have sodium inside, a very small amount. So they're always looking for sodium. And it's so important. So our body, we have a hormone. Their function is for sodium reabsorption. It's called aldosterone. So that means sodium is a very important molecule because when you don't have sodium, no action potential. You need to have sodium. It's in the past 100 years, past the 50 years, and people found when they put more sodium into the food, they can keep the food for longer. And the sodium also make the food delicious. So they will put a lot of sodium into the food they make. So the food industry, they don't have your health in their priority. There is a business. They're all about making money. They just have too much sodium. And too much sodium creates some problems like hypertension or other problems. So in your body, in your kidney, the first one to take back is sodium. Because when you take sodium back, the N ion, the negative charge ion follow. And after the N ion follow, water follow. Water always want to go to dilute those ions. And after water follow, those other ions, urea, they follow. So in those 20 marbles, the first one you take back is sodium. After you take sodium back, all the others come back. So let's look how to take sodium back, the molecular mechanism. The molecular mechanism is actually what you learned in Unit 1, transport sodium. So here there's a review, right? And in Unit 1, I teach you, okay, first, figure out which direction they move. Second, figure out their concentration gradient. Because once you have these two, you know which membrane protein you're supposed to put on the apical side and basolateral side. So this is apical, this is basolateral. Reabsorption, it goes from the lumen. So this yellow part is the lumen. It will go into the cell, then go to the ECF, interstitial fluid. So this purple side, that's the ECF, that's inside the body. So reabsorption means go from this yellow through the apical membrane, through the basolateral membrane to the purple. That's the direction. So that's the first one. Then second, let's look at the concentration gradient. Sodium, low outside, low inside, high outside. So inside the cell, low sodium. In the lumen, in the ECF, high sodium. Okay, we have everything we need. We know the direction, we know the concentration gradient. Now let's look at what the membrane protein we're supposed to put on the apical, on the basolateral. So on the apical side, you move from the lumen into the cell. It goes from high to low. Oh, high to low. Concentration gradient is the driving force. So all you need is passive transport. So on the apical side, you put sodium channel. And now the sodium move into the cell. You want the sodium move from the cell into the interstitial fluid, move from low to high. You need active transport. So we put sodium potassium pump on the basolateral side. We use ATP as an energy source and pump sodium from low to high. Now you finish this job. So the kidney use a lot of ATP. Then you put a potassium leak channel to balance the concentration gradient of potassium. So that's the mechanism for sodium reabsorption. Now let's look at glucose. Glucose. First, figure out their movement. And glucose, we want to reabsorb glucose. And actually, we want 100% reabsorption. You filter in 20 glucose. You don't want to just take 16 back. You want to take all 20 back because you want to know glucose stay in the lumen. If you have a glucose stay in the lumen, it will go to the bladder, you pee it out, diabetes. So you want 100% glucose reabsorption. You take all the glucose from the lumen, go into the ECF. So that's glucose reabsorption. So we figure out the direction from the lumen into the ECF. Now let's look at the concentration. Glucose, high inside, low outside. So glucose is low in the lumen, high in the cell, low in the ECF. Okay, we figure out the direction, we figure out the concentration gradient. Let's get started. Glucose, low in the lumen, go into the cell from low to high, active transport. And these cells is use a lot of ATP. So you always try to save some ATP. You will try to use other energy source instead of ATP. So it use the concentration gradient of sodium as the energy source. Since it put effort into moving the sodium all the time, just take advantage of the sodium. So use the concentration gradient of sodium as the energy source to move glucose from low to high, secondary active transport, indirect active transport. Then the glucose need to move from the cell into the ECF, from high to low, passive transport. So you put the glucose carrier on the basolateral. And you also put the sodium potassium pump to balance the ion concentration and the potassium leak channel. Okay, job done. And in unit 1, when we talk about the glucose carrier, glucose transporter, ion channels, I told you very important concept. If it's ion channel, the channel remain open, the ions move through. The more ions you have, the more gonna go through. Because they don't have binding site. We don't have to worry about saturation in the normal physiological situation. But for glucose carrier, for the pump, for the co-transporter, symporter, antiporter, they all have binding site. And when they have binding site, they can be saturated. And I use the UT shuttle as an example. Say this UT shuttle have 40 seats. Okay, if you only have 2 students, well, they can take 2 students away. If it's 39, you can take all 39. But when you have 41, they can take maximally 40. The less students have to wait for the next shuttle. Saturation. So for glucose transporter, they have to worry about saturation. Because you can have way too many students and all the shuttles, they are full. They could not transport glucose anymore. Some glucose is gonna go through this and show up in the urine. That's diabetes. So diabetes patients have to watch their blood sugar level. They don't want their concentration of glucose to be too high and go over this. And that threshold, let's say 40 students, right? That's the threshold. That concentration is called the renal threshold. That's that concentration. So why diabetes patients have to watch their blood sugar level, have to measure their blood sugar, not every day, every meal, before, after, because they want to make sure their blood sugar level never go over the renal threshold. Okay, let's look at this. Renal threshold transport maximum. So you know those transport proteins, they have binding site, they can be saturated. So we can have the transport maxima, we can have the renal threshold. So renal threshold and transport maxima, they happen simultaneously. They just tell you different things. These tell you the transportation graph, the x-axis, that's the concentration. This is how many students you have. The y-axis, that's the transportation rate. That's how many students can be transported per minute. So it depends on the UT shuttle, depends on the membrane protein. So if you have no students, great, no student need to be transported. So when diabetes patient, just tell them, you have no blood sugar in your blood, problem fixed. Yes, problem fixed, but he's dead. You need to have blood sugar. So when you have two students there, yes, 2 students can be transported. When you have 3, they can be transported. When you have 4, okay, that's the maximum. When you have 5, only 4 can be transported. 1 have to wait. When you have 6, 4 can be transported. So this concentration is called the renal threshold. And the renal threshold is the concentration. So at this moment, the maximum transportation rate is called the transport maximum. And that's what happens. We have filtration, we have reabsorption. And the difference of these two, that's the excretion. For glucose, we want the excretion of glucose to be 0. We don't want to pee glucose out because you have sugar in your pee. That's diabetes. 100 years ago, that's how doctor checked diabetes. They just pour those urine on the floor. If ants come, oh, they have sugar inside, diabetes. You want the excretion of glucose to be 0. And you say, if I don't put anything in, problem solved. Yes, but you have to put it in because the blood sugar level is not 0. This is not 0. You say, I make this 0, problem solved. Yes, no students, you don't have to transport. The problem is the blood sugar level. You need blood sugar because your brain needs sugar. So this is not 0. And then how many? Well, filtration rate is fixed. So if your filtration rate is this, you have 1 marble per liter, or 2 multiply 1 is 2. And if you have 2 marbles per liter, well, that's 4. Right? Per minute, you filter in 4. And if you eat cookies like crazy, you're in bad mood, you eat the whole cake. Sometimes you watch the TikTok, they show that, you eat the whole cake. And you have 40 here, 40 multiplied by 2, that's 80. Okay, linear relationship. And you really pray your shuttle can take all of them back. And the renal threshold is when the filtrations reach maximum transportation, reabsorption. And the maximum reabsorption is transport maximum. So transport maximum is one of the reabsorption. That's the maximum they can do. And you found this concentration here. At that moment, we call the renal threshold. Still this equation. So the concept is pretty straightforward. Is when we start to put real numbers in, students start to figure out. But this is concept. How much we dump in equal to how much we can take back. And when this whole thing being pushed to their limits, the transportation rate, we call the transport maximum. And this field concentration, we call the Renal threshold. And still no excretion. So that's when the filtration equal to reabsorption. Because when you take how much you filtered in, subtract how much being reabsorbed, equal to how much you get here. Next time we talk about this. I dump in 20 marbles, I only get 10 because 10 been taken back. And this time is I dump in 20 marbles, I want to get 0 because glucose 100% taken back. So that's when these two are the same, when the excretion rate is 0. So the concept is pretty straightforward. Is when we put those numbers in, student freak out. Now let's do a practice. I give you the transport maximum of 360 milligram per minute. So this is 360 milligram per minute. I give you the GFR. That's the filtration rate. 120 milliliter per minute. That's the GFR. And I ask you, what's the Renal threshold? Renal threshold is the concentration of that molecule in the plasma. We just call it the Renal threshold because it's been pushed to its limit. It's the Renal threshold. So this is the Renal threshold. And the rest is math. So math is not that difficult. So we figure out the Renal threshold is 3 milligram per minute. Perfect. This is the unit for concentration. This tells you your calculation is correct. And this is how we figure out the Renal threshold. It's just a concentration. The concentration can be 2 milligram per ml. Yeah, we don't call the Renal threshold because you haven't reached the threshold yet. It can be 1 milligram per ml. And probably you're going to feel hungry, or your blood sugar level becomes so low, you feel hungry. But well, still your kidney can handle it. And you can say this is 0 milligram per ml, then nothing going to happen. Perfect. The problem is this person is dead. You need to have blood sugar. So that's this whole thing. The concept is this. So when I do the renal calculation, I usually draw a small net from there. It helped me to visualize the concept. And you should come here, take the test, so I can draw some. It's more difficult to draw them on the with the scratch paper functions on the online test. So that's how we calculate. Any questions? So we use this to explain how to use the Renal threshold, how to use the transport maxima to calculate the Renal threshold. And your discussion exercise, you have one discussion exercise completely dedicated to calculate everything. That's the Renal calculation. So let's look what happens. Not just reabsorption. All processes happen in the kidney. You say, oh, there's a lot. Well, actually, not a lot. Only 4 processes: filtration, reabsorption, secretion, and excretion. Excuse me. And most of the time we deal with 3, not 4, because the kidney either handle this molecule as net reabsorption, like glucose, you want 100% taking them back, or net secretion, like penicillin. Net secretion. You dump in 10 marbles, you found why I get 20 there, because well, you secrete another 10. Or neither reabsorbed nor secreted. And we love those molecules because how much filtered it equal to how much you get it. And that's inulin and creatinine. And we love them because we can use them to calculate GFR. So most of the time we deal with 3, not 4. Or if you're lucky, you deal with 2. Inulin, creatinine, we deal with 2. So only those 3 processes. And here we talk about glucose. Let's look at glucose. Glucose is handled as reabsorption. And we want it to be 100% reabsorbed. We want the excretion to be 0. We don't want to pee glucose out. So filtration equal to reabsorption. So we create 3 figures. We present filtration, reabsorption, excretion. And the x-axis, all of them, concentration of glucose. So let's look at the filtration first. Filtration, non-selective. It just creates sleet. And the more you have, the more will be filtered in. It's like ion channel. Okay, the more you have, the more going to go through. All you need to ask is, would this molecule go through the sleet? If this molecule is too big, well, filtration, 0. Like red blood cell. If I ask you the red blood cell filtration rate, you don't have to calculate. It's 0. Because red blood cell is too big to go through the sleet. Only in those very abnormal situations, you damage those podocyte cells, sleet, and you start to have red blood cells. Excuse me. You start to have red blood cells show up in the urine and you pee blood. but most of the situation that zero. And glucose, glucose can go through the sleep. So it will be filtered in. If you have no blood sugar, nothing being filtered in, that's perfect. Well, that's not perfect. That's you have no blood sugar. But we all have blood sugar. So when you have 100 will be filtered in, 200 will be filtered in, 300 will be filtered in. It's a linear relationship because it's non-selective. So the more you have, the more will be filtered in. That's why diabetes patients, they have to watch their blood sugar because this is very dangerous. For diabetes patients, they eat a whole cake. All these 500 blood sugars will be filtered into the kidney. Then the kidney have to handle all these 500 sugar. And they can overload the kidney, eventually cause kidney failure. They need dialysis or they need a new kidney. So that's filtration, linear relationship, because it's non-selective. Now let's look at reabsorption. Reabsorption depends on the membrane protein. It's selective glucose, where we have a lot of glucose protein to transport glucose. Your body needs glucose. And those proteins, they have binding site, they can be saturated. So they have the transport maximum. And that concentration is called the renal threshold. So you have to make sure your blood sugar level don't go over the renal threshold, because before the renal threshold, the transportation rate and the concentration of glucose, linear relationship. Until it reaches the renal threshold, here is 300 milligram per 100 milliliter of blood. It starts being saturated, it reaches the transport maximum. And when you reach the transport maximum, you start to pee glucose. Right? So you want to make sure the blood sugar level stay below renal threshold, 300 milligram per 100 ml of blood. And for you, all of you, you're pretty healthy. You say, well, next week, Thanksgiving, I'm going to eat the turkey. Then I love the stuffing. And you eat the stuffings. You say, oh, pie, let's eat the pie. And you drink Coke. And you eat donuts. You eat cookies. Would you push your blood sugar level to here? Probably not. You're young, you're still healthy. Your body have a very good weapon to fight this, which is called insulin. Your body have insulin. And your digestive system is waiting there to handle this. So before the food go to your stomach, you smell the food, you see the food, sensory system. We'll talk about the unit 2. We send the signal through the cranial nerve number 10, vagus, go to your GI tract, ask them, hey, get ready. So those digestive enzymes waiting there, and when you eat the food, your blood sugar level start to increase, trigger insulin release. And insulin will go to your whole body because it goes to your blood. And the insulin receptor is in the skeletal muscle. Skeletal muscle is the main target. And you have a lot of skeletal muscle. They will take glucose in. When they take glucose in, your blood sugar level drop. It won't reach this. That's why in this area, this gray area, most people, their blood sugar level stay between 100 to 200 milligram per 100 ml of blood per decimal liter. So when they do those diabetes patients, they check the blood sample. If the number is between 100 to 200, that's normal. So after meal, the number goes a little bit higher, should not go over 200. And when they're hungry, it should not go lower than 100. That's the normal range. So you're pretty young and healthy, your blood sugar level should always stay in this range. Diabetes patient, they can go over. They can also go under. You won't go under because you have, you have glucagon. So when you're hungry, you say you forget to eat breakfast. Or if you're hungry, but your glucagon release, your blood sugar level won't drop to this low. Diabetes patient, their blood sugar can be dropped to this low. It's not just insulin's problem, it's their blood sugar regulation is all messed up. So they can become too high if they eat too much carbohydrate. And they can also go to become too low and they can pass out. It's like the whole system is being messed up. And diabetes patients, they have to carry some sugar, candy bar, some sugar for them. If their blood sugar level become too low, they have to eat, make sure the blood sugar go to this range. And your blood sugar level should be maintained in this range with your insulin and glucagon. So if the blood sugar level is in this range, all filtered in will be taken back. Your excretion of glucose is 0. So let's look at the excretion. Yes, it's all 0 here. And for most of you, your blood sugar level stay in this range. Well, you never have to worry about excretion of glucose because that's 0. Until your blood sugar level reach the renal threshold. That's when this is made. When you start to go over the renal threshold, you start to have excretion because the transport maximum, you reach the transport maximum. So you found after the renal threshold, you start to have excretion. And it's a linear relationship because this you reach the maximum, you take the filtration substrate out this equal to excretion. That's a linear relationship. The more you filter it in, the more will be excreted out. So the mass part and the picture part explain the same thing. That's when you put those 3 lines together. The red line, filtration. The green line, reabsorption. So before they reach the renal threshold, these two lines completely overlap because for glucose, 100% reabsorbed. How much you filtered in, how much need to be taken back. If they are not taken back, you have glucose in the urine. So when you take the red line, substrate green line, you get 0 because in a normal situation, your excretion of glucose is 0. And hopefully for your whole life, you stay in this range. You never had diabetes. You always stay in this range. But when the blood sugar level becomes too high in diabetes patients, they reach their transport maxima and their filtration is higher than the reabsorption. Okay, subtract these two, they start to have excretion. And the more blood sugar they have, the more being filtered in because it's a linear relationship. And the transport maxima is reached, the more glucose will be excreted out. And those high blood sugar, they lose sugar, so they feel hungry, they'll eat more. And those blood sugar, not blood sugar, those urine sugar, not the sugar in the urine, will trap water, so they pee more. So diabetes patients, they pee more, they eat more, and they feel tired more. And the situation just gets worse and worse. Okay, that's glucose handled. Any question? 3 more minutes. Yes. Yes, because we're talking about glucose handle. Yes, each molecule, your kidney handle them different. Yeah, that's a good question. We're talking about glucose. So for other molecules, your kidney handle them differently. Penicillin, you can expect the excretions will be much higher than the filtration. Yeah, the excretion will be around here because penicillin is net secretion. Good question. And for the creatinine and inulin, this will be 0. Because creatinine and inulin is how much being filtered in, how much being excreted. So for creatinine and inulin, this blue line will perfectly match the red line. And no reabsorption. Inulin, this one is 0. Yeah, kidney just handle different molecules differently. That's a very good question. Okay, any other question? So Tuesday, we still have class. I don't know how many of you are going to show up, but I will still be here since the syllabus say we have class. I just follow the syllabus. So Tuesday, I will still be here. Then one more class after, then we're done. So tomorrow I have office hour. Next week.